All right, so now that we know what the stress tensor is, we can start playing with it in order to derive some very useful equations. The first one is going to be the Cauchy equation of equilibrium for continuum mechanics. So what we're going to do is we're going to see what are all the stresses that are acting on this cube. And for this particular example, we just work with the direction number 3. And if you remember from your static class, in order to have an object in equilibrium, you have to add all the forces and to add them up and to make them equal to 0 or equal to mass equal acceleration. All right, so let's start by identifying the stresses. On the bottom face of this cube, I'm going to have the normal stress sigma 33, which of course is going in direction 3. On the top face, in order to equilibrate that stress, I'm going to have the same stress, but I'm also going to have a small gradient of this stress in direction 3, which is written in this way. The second term is that additional increment that I might have in going from one phase to the other in a infinitesimal change delta x3. So here, from here to here, the distance is the x3. All right, in direction 3, notice that we also are going to have shear stresses. For example, the stress here on the negative phase, this is going to be sigma 23 is a shear stress, and on the opposite phase, I'm going to have sigma 23 plus the infinitesimal variation with a change of distance dx2. And the same thing is going to apply for the other shear stress on phase number 1. So on the back, this is getting a little bit difficult to draw, but here on the back, I'm going to have sigma 13, and on the front, I'm going to have sigma 13 plus the infinitesimal variation in direction 13 because of the change of length in direction 1. And what we're going to do, I'm going to do is to add all of these forces together, and we'll make them equal to 0. There is one more component which I'm going to add over here, and this is going to be what is called a body force. And the body force, let me see, I'll do it with gray, is going to be a property of the entire volume. And let me make this go in the positive direction, and we're going to call it F3. All right, so if I want to add all these forces, notice that I'm going to have to multiply the stresses by the areas in which they are applied. And these depend on the lengths dx1, dx2, and dx3, which I'm here writing right now. All right, so let's start with the normal stresses. The normal stress, for example, sigma 33, is applied on the phase number 3. The area phase number 3 is dx1 times dx2. It's going in positive direction. If I want to add the one on the top, it's going to be sigma 33 plus infinitesimal variation um, times again the same area. all all I have done so far is to consider the normal stresses. Now let's add the shear stresses. Same thing with the shear stresses. Sigma 2, 3 now is applied on face number 2, and this area depends on dx1 times dx3. On the opposite side, I have the other stress going in the other direction with its infinitesimal variation, again times the area of the face, and I have one more shear stress to add, that was in blue, sigma 1, 3, and the area of that is okay, I just found one tiny mistake. No, this is fine. All right, I found it. Let me correct this before we continue. This is not dx2. This is dx1. Dx2 is over here. Okay, so this is dx2 times dx3, and the same for the opposite stress on the opposite face. All right, there is just one more thing to add over here, and this is going to be the body force, and the body force in direction 3 is going to be just let's just denote it for now as F3, and all of this is going to be equal to 0 or y0, because I'm assuming here that there is no acceleration, so this is 0. So even if there is a mass, this is going to be 0, and therefore all of this has to be 0. All right, so I like that you notice that the volume of this element is actually the product of dx1, dx2, and dx3. We're going to use this in the equation in order to solve what I have over here. Okay, I would also like that you notice that since sigma 33 is equal to sigma 33 in this case, and they are both multiplied by the same quantity, these are going to cancel out. So this is going to cancel out. Sigma 23 is going to cancel out. Sigma 13 is going to cancel out. And all are going to be left with are the infinitesimal variations. And notice that also the infinitesimal variations are multiplied times dx1, dx2, dx3 in all cases. And that just helped me discover one type over here. dx3, dx1, dx3, and therefore I can write my equation as now just the infinitesimal variations times the volumes dx1, dx2, dx3, and plus the infinitesimal variation of the shear stress, also dx1, dx2, dx3, infinitesimal variation on direction x1 of sigma 1, 3, dx1, dx2, dx3, and that times that plus the body force F3 should be equal to 0. And since you can notice this is a common factor, dx1, dx3, and therefore this equation is just going to simplify to the partial derivatives. I'm dividing by dx1, dx2, dx3 everywhere, and therefore I'm going to have here a force by unit of volume equal to 0. And I can do, this is the result for equilibrium of forces in direction number 3, but I can do the same thing also for equilibrium of forces in direction number 1 and number 2. And the equations are pretty similar. So if I were to do that, I'm going to arrive with what are called the Cauchy's equilibrium equations for continuum mechanics. And these equations are going to be very useful for the rest of our class. These are going to be 3 equations, and I'm going to write the first one, the last one, which is the one that we derived, and I'm going to change it a little bit, okay? But it is the same thing. You remember that we said that the shear stresses are equal to each other or are symmetric, so that sigma 1,3 is equal to sigma 3,1, right? So the same equation, then I can write as the variation of sigma 3,1 in direction 1 plus the variation of sigma 3,2 from this term over here with a variation in distance 2 plus the variation of the normal stress sigma 3,3 with variation 3 plus a body force, which here I'm going to refer to the body force. This is a force by unit of volume, and it's very useful to express this through density and through mass. So I can write the same thing as V3 times the mass density, which is the mass of the object divided by volume, to be equal to 0. And this will be the equation for direction number 3. But I can do exactly the same thing for all directions. And what this is going to look like is something like this, with the same pattern. And it's a little bit easier to remember written in this way. This is going to be 1, 2, 1, 2, 1, 3 plus the body force in direction 1 times mass density equal to 0 and sigma 2, 1, sigma 2, 2, and sigma 2, 3 also equal to 0. All these partial derivatives and this entire differential equation is what is called the Cauchy's equilibrium equation or equations. In this case, if you have three, because we're talking in 3 dimensions. There is a shorter way to write these equilibrium equations, and it looks something like this. A partial derivative of the tensor, and this is written in what is called initial notation. I'm not going to ask you to learn this right now, but as we continue with the class, you will see that you are going to get a little bit more familiar with this type of writing equations in 3 dimensions when there are many indices, and also can be written in more of a vectorial form where the divergence of the stress tensor is here. This is plus or minus, it does make a big difference, depends on your convention, times the body force, which is a vector, times mass density equal to 0. These three are the same equation, okay? And it's called the Cauchy's equilibrium equation. To give you an example, the body force, if for example we had gravity in direction number 3, then V3 will be equal to G. And if we consider that 3 is going up, then that's going to be negative G. That's going to be gravity. There are other examples of body forces. For example, you could have an electromagnetic body force, or you could have a viscous drag body force. Gravity is the most common example. All right, so we're going to come back to this Cauchy equilibrium equation because we're going to use it quite a bit. This is one of the 3 equations that we're going to use a lot in this class. But just for now, let's see an application of the Cauchy's equilibrium equation. For this particular application, what I'm going to do is I'm going to assume that I have a infinite half space where this top surface, we can assume that as a free surface and that to be the ground. I'm going to add here a coordinate system, 1, 2, and 3. And I'm going to consider that 3 is the vertical direction. All right. I'm going to use the Cauchy equations so that I can solve what is the change of stress as a function of depth. And let me here just grab this and do a copy and paste. All right. So same equations that we just derived. And what I'm going to do is I'm going to start simplifying this equation so we can solve what we're looking for. All right, so the objective is going to be to find out what is the variation of stress in vertical direction with the variation of depth. And for that, we're going to do a few things. First of all, I'm considering that this is what is called a half space. And what that means is that everything is the same in direction 1 and 2. So any derivative in direction 1 or in direction 2 is going to be equal to 0. And as you can recognize in this equation, this is going to be equal to 0, this is going to be equal to 0, and all I'm going to be left with is with this equation over here. So if I want to solve for that equation now, I'm going to have that the variation of horizontal of vertical stress with direction 3 is going to be equal to the body force, which in this case is going to be gravity times mass density, which is rho. And if I want to solve this equation, what I'm going to have to do is I'm going to have to integrate and to solve by parts. All right. So I'm going to pass this derivative or this differential to the other side, so that the variation of sigma 33 is going to be gravity times density times dx3, and I'm going to integrate this from the surface where x3 is equal to 0. Let me be a little bit more detailed with that, until the depth x3, and this is going to be the same. And here this is going to be x3 equal to 0 till x3, and actually, to be precise, let me modify slightly this. This is going to be from sigma 33 at x3 equal to 0 to sigma 33 at x3 equal to x3. So this is a very easy integral, and if I assume that the stress on the surface is equal to 0, so we're going to assume that this is also a free surface, and therefore sigma 33 at x3 equal to 0 is 0, then this integral is going to be simple. It's just going to be sigma 33 at x3, and the integral of this is going to depend. Let's start now with just a general case. If I go from 0 to x3, gravity, we can assume that's a constant. Density, that may not be a constant, maybe a function of x3, so I cannot take it outside the integral right away, with the differential of x3. And I'm going to do one more thing over here, and if we talk in practical terms, sigma 33 is going to be the vertical stress, and I can write this as SV, total vertical stress, and let's use, instead of x3, to be also a little bit more practical, just let's use Z for depth. The vertical stress as a function of depth is going to be the integral from 0 to the particular vertical depth that you're considering of G times the bulk density of the rock, that includes everything, minerals, fluids, everything, as a function of depth integrated with depth. And this is the general equation for calculating vertical stress in the subsurface, and we derived this one from the Cauchy's equilibrium equation. This is just one easy solution for that. All right. One practical comment here to take into account that notice is that, and let me add it here, that here Z is vertical depth. Very often in the field, we have wellbores which are not vertical. And many times in the field, the data that we have comes from well logs in which the depth is not in terms of vertical depth, but it's in terms of measured depth. So it is very important that when you actually compute vertical stress, you consider true vertical depth and not measured depth. So for example, if you want to calculate what is the vertical stress at this location, what you have to consider is what is the true vertical depth from the ground, TVD, true vertical depth. This is going to be Z in the equation that we have here on the right, and not measured depth. Measured depth is going to be the length of the line that goes along the wellbore. All right. We're going to be talking a little bit more about this in the application problems and when we work in the hands-on problem. But I have one example to show related to this, and it is right here. This is what is called a horseshoe-shaped wellbore. So you see it starts on the surface, it gets a little bit deviated. When you get to the base zone, it goes horizontal, it makes a U-loop and comes back. If you want to calculate vertical stress at this particular location, remember that you're interested in the true vertical depth and not in the measured depth that you get along the wellbore. We're going to see that in order to calculate true vertical stress for real wellbores, we're going to have to combine these two quantities, measured depth and true vertical depth. And that's going to allow us to calculate this vertical stress. Just one more thing before I forget. Uh, let's assume the particular case in which mass density is a constant. In this case, if the mass density is just equal to one value, then the vertical stress, and this could be for an onshore location, is just going to be equal to that value of density times gravity times depth. It is a quite simple equation. And if we think in terms of gradient, what is the change of vertical stress with change of depth? This is going to be the density of the rock times the gravity constant. And for onshore conditions, this is usually what it may also be valid offshore, as long as we're talking about a gradient. In international units, this is about 23 MPa per kilometer, and in field oil field units and English units, this is about 1 psi per foot. So now you see why this gradient it comes to this value. I leave this as a homework to you. I obtained these gradients assuming a bulk density of the rock of 2,300 kilograms per meter square. And of course, G is 9.8 meters per second square. You can do the math and you can calculate these gradients and you can prove that these are typical gradients for vertical stress. And this is the one that we used in the previous video. All right, then with this, I end this lecture, this part of the video, and we're going to continue talking about vertical stress in another